Okay, good afternoon. Welcome to the ASHRAE New York March Designer Series. My name is Ben Rodney, and I'm the president of ASHRAE New York for 2021-22. I am very happy today to welcome our speaker, my good friend, and one of the leading voices on sustainable design in our city for a number of years, Jeff Rios. So Jeff, thanks for being here today.
Thanks, Ben. Yeah, looking forward to it.
Yeah. For those who don't know, Jeff is a partner and co-director of AKF's Energy and Performance team, specializing in increasing energy efficiency within new and existing buildings. He's highly valued for his experience as a mechanical engineer and his expertise in energy modeling platforms. Jeff is a collaborative member of the team, working closely with engineers, designers, and architects to provide thoughtful, results-focused solutions, and has shared his expertise at Greenbuild on well building, at Urban Green on New York City energy codes, and is as a continuing lecturer at Cooper Union. Jeff also serves as a member of the ACEC Metro Region Energy Code Committee, as well as the New York City DOB Energy Code Advisory Committee, and has presented on numerous ASHRAE New York panels in the past. So really appreciate him being here today. Before we get started, I'd like to go through a few announcements for ASHRAE New York. This is today's designer series. So our next, the next episode of the ASHRAE New York Designer Series is in May. It'll be featuring Bjarni Olesen, who was a former ASHRAE Society president, speaking about applications of radiant heating and cooling systems in buildings. So he is a distinguished lecturer for ASHRAE, speaking at chapters all over the world. So we're very pleased that he'll be joining our New York chapter live from Technical University of Denmark. So please, please sign up for that on our website. On March 30th, we do have a scholarship information session. If you are a student or know any students that are interested in an ASHRAE scholarship, please sign up for this event. So we'll be going through the details of that. And then on May 20th this year is our annual gala. We have not had the ASHRAE Gala since 2019. This is a wonderful event with people from all over the HVAC industry getting together to celebrate the year. We're also going to be honoring our Distinguished Service Award winners, Edward Piconich from SL Green, along with Gina Bokra with the New York City DOB. And this will be at Gotham Hall as a casino night. Should be a lot of fun. And we'll also be supporting our charitable partners, Tunnel for Towers and Non-Traditional Employment for Women. So check out our website to find more information on that. And then we're also doing our membership battle. So if your firm wants to support your employees and sign up for ASHRAE memberships, the firm that signs up the most members, most gross members between January 1st and April 15th will receive 5 free tickets to the gala, and the highest percentage increase for a firm in new members will receive 5 free tickets for the gala. So you can find out all about joining ASHRAE on our website or the Society's website, so please do that today. And the other thing I want to mention is we had a cancellation for our April dinner meter speaker. So if your company has an interesting topic and you'd like to present a 1 PDH credit at our April meeting, please reach out to me at ashraenyc@gmail.com. Again, April dinner meeting, ashraenyc@gmail.com. Today's presentation is worth 1 PDH credit. So to receive your PDH, please wait for the survey to pop up after you exit the presentation today. Make sure to turn off your pop-up blocker, and then we will send you the certificate within a few days. And this video will also be recorded and available on the ASHRAE New York YouTube channel. So make sure to subscribe and turn on notifications on the YouTube channel so that you'll receive the recording of this video. And if you have any questions today, please put them in the chat, and we will ask Jeff questions periodically throughout the presentation. And with that, I will hand it off to Jeff.
Great, thanks, Ben. Just gonna make sure I have the go. Okay. All right, is that up screen up there, Ben?
Yes.
All right, perfect. So thanks for joining, everybody. Thanks for the intro, Ben. The presentation today is going to talk about, as the title here suggests, designing without fossil fuel. So we'll kind of get into that. I'm gonna kind of talk a little bit about what that means, which is essentially building electrification. Talk about what it is and why we're talking about that. Some of this may not be news to all of you, but I think it's good to do a quick sort of level set and start the conversation as to what we're talking about and why. Then we're going to walk through our process. I want to talk about why certain clients are prioritizing this, what we're experiencing, what's really driving this discussion, which is a pretty substantial change from the way we design buildings for thousands of years with fossil fuel or just essentially burning something to heat, right? So it's a big shift, and we'll talk a little bit about why that shift's happening and what our process is to kind of walk clients through the alternatives and what it means to their project. I'll cover technologies a little bit. There's lots of technology presentations you can get from vendors. I'll just give a little bit of a background on some of the technology changes that we've experienced in the last few years while designing these buildings. And then I'll walk through a couple of case studies. It's essentially two case studies that are very similar buildings, but with some key differences. And I'll talk about why, what that meant for our designs, and sort of how we dealt with that and how we walk through that. So diving right in. Again, starting with the how and why, just sort of the background on it, right? So most of you are familiar with electric cars being a positive environmental cause and something that's good for the environment and low carbon, right? That's been around for a long time. People have kind of been talking about that for at least the last decade when Tesla started making their first few models. That's a pretty known quantity and what that means. And recently, within the last several years, buildings have really started to shift that direction. To kind of set the stage as to why that's different, why buildings are a little bit lagging in cars. It's pretty simple math, but I think I always find this helpful for myself to kind of like remind myself what it is we're talking about and what the difference here is and what we're trying to do with a building, within a building when we're talking about heating with electricity in an efficient way. So as I think this is a group of engineers likely, right? So electric, we always used to make the joke, electric is 100% efficient or 100% inefficient. When we were talking about, just electric fin tube radiators, it is 100% efficient essentially, right? You put in a kW, you get a kW heat output for the most part. That's true in a car and a building, right? The difference comes into what a car is doing. If you're the alternative, the fossil fuel gas alternative is, a car has to burn that gas and generate energy in a way that moves the wheels, right? That's a much more complicated process. Probably a lot of us remember our IC engines class and back in college. That's a lot harder to do than is just burning something and heating with it, right? So like as a comment here, it's easy to heat with fire, right? Humans have been doing this since the dawn of time. So it's a lot simpler to create an efficient heating source with a fossil fuel system than it is to move a car, right? So what that means what that's meant historically is that because the gas alternative for a car is so inefficient to burn the gas, most electric grids throughout the country it's been beneficial from a carbon standpoint and overall source energy standpoint to use an electric car versus using a gas burning car, right? It's all about where the source energy comes from, and most source energy on the electric grid in the United States is still largely fossil fuel based. On the building side, if we were to just do an electric resistance heating system in almost all locations within the US, that's a less carbon efficient system than is burning fossil fuel within the building, especially if you're talking about condensing boilers, right? So to level set, that's the difference between these two things, and really why what we're talking about today is an electric building. And the short-term study and short-term conversation is an electric heat pump system, because what that means is this is a number specific to where we live and work in New York City. If you have a heating system with a COP, so there's the heat pump heating system with a COP of 1.6 or better, and it's somewhere in the 1.6 range. That is a better carbon emitter per BTU of energy than is most natural gas systems, right? So an electric resistance system is a 1.0 COP. That is not better, but a electric heat pump system is better from a BTU to BTU, or excuse me, a carbon to BTU standpoint. So that we can do this today, and we can do this efficiently today. And the other important thing to note is that's today's grid. But the reality is, and many of you have heard the news on this and heard discussions on this, that our grid is there's ambitious goals at the state and city level, and our grid is likely to improve significantly in terms of the amount of renewables on it in the very near term. If you look here at the graphic I have up there with the blue bars, that image is taken from an NREL tool called Cambium, which is available. You can see the link on the bottom of the page here. It's really a super fun tool. They basically have mapped out any state in the country. You can go in there, you can play with different test cases, and you can predict. There's a lot of different options to look at, but effectively what this is showing here is the average carbon consumption per kW produced on the grid, right, or per megawatt produced on the grid. So what this is showing, if you look at this very briefly, this is New York State. It's not city specific. It's for the state. That the tool is set up by state. This is what is called within the tool the mid case, which is essentially, sort of like the average expected case going forward. And you see a pretty significant drop from what it was in 2020. If you can see all the way on the left, that was a 2020 number. You see the little blip up. Many of you might guess that's when Indian Point closed, right? So we did increase the carbon on the grid for New York State when Indian Point closed. But then significantly after that, there's a significant reduction after that based on what is expected and actually what is already planned in terms of offshore wind capacity, new PV generation on the books for the state, and distribution systems that are coming online in the next 10 years, right? That is expected. Also within that is kind of pulling natural gas resources off the grid. There's lots and lots of conversations to be had by people that are much more in the know than me on that, so I'm not going to say too much more. But what this is telling us is that the predictions here are real and based on measurable projects that are known. And the green line that we've shown here is a very, very simple, sort of a dumb linear representation of the New York State legislation set in place goals back in 2019, the summer of 2019, to reduce the carbon, or excuse me, increase the renewable energy on the New York State grid such that it was 70% renewable by 2030 and 100% renewable by 2040. So basically what that is we kind of said, all right, well, in 2020, it's this, it's gonna be 0 by 2040, draw a straight line down, that's what it looks like, right? So, that's not meaningful other than it's just in line with what the legislation is proposing. But what is interesting here is the Cambium tool is predicting a very, very similar curve. And the Cambium tool is not strictly based on just the legislation. It is based specifically on projects that are on the books. So at least between now and 2030, there are realistic projects and realistic infrastructure being planned that will get us to that 2030 goal, right? So that's a very important component here, because if you overlay this red line, this red line is roughly, I'm not going to say I did a very scientific analysis here, but that 1.6 that I mentioned earlier, which is the 1.6 COP, where at which point an efficient heating system is better than a natural gas system. At that point, when the grid gets that good, so what it's showing now is somewhere around the 2027, 2028 timeline, if the grid hits that target in terms of the amount of renewables on the grid, an electric resistance system will be better than a gas system, right? So that is not today, we're not there yet. We've probably got 5 to 10 years before that becomes reality. But this is just to say that in the future, electric really is going to be the carbon, the better carbon solution relative to natural gas heating systems. And this is all sort of what's in play within a lot of the legislation happening, both at the city and the state. So again, this is all just to set this sort of background and sort of why electrification matters and what it means to the buildings that we're working in. So just to touch briefly, I think I mentioned legislation a few times in that last couple slides, but what's driving it? I mean, obviously the very first thing that's driving it is climate change, and the legislation is based on really the necessary planning to sort of try to limit climate change's effects, right? But it's specifically what's resulting from that, and I have 3 pretty key things up there now, but there's lots more planned and lots more happening elsewhere outside of the areas we work. But legislation, and most of this to date has been happening at a local and state level. Specifically, the 2 ones that we probably talk about the most here in New York are Local Law 97, which is the building emissions limits. I'm sure many of you are familiar with that. We've had lots of great ASHRAE and other presentations on that topic, but that's really the first thing that started driving this, and that goes back now almost 3 years to 2019. When that was first written, that really is a pretty substantial sort of impact to what buildings need to do over time, and really is the way it's looking at carbon emissions is long-term going to be pushing electrification as the right solution for buildings. The second bullet point there, the New York City Local Law 154, which just passed at the end of 2021, so just got signed into law right before this year. That is essentially not allowing new gas hookups for many buildings in the city, starting in 2 years from now, in the end of 2023, for smaller scale buildings. That's not going to be allowed. And as of 2027, for pretty much any building in the city, there are some exceptions for use types, but the vast majority of new buildings within the city are not going to be allowed to get a gas hookup. In the next few years, this presentation and this conversation is not going to be about options and why and what we want to do. It's going to be about, okay, this is what we have. This is how we design buildings now in New York City, and this is what we have to be thinking about. Similarly, Boston has legislation right now. It's BERDO 2.0 is the legislation that's in effect. It is very similar in a lot of ways to Local Law 97 in New York, where it's setting carbon emissions limits for buildings within the city, and really, again, in a very similar way, starting to target natural gas as a negative and moving buildings towards an efficient electric solution. So that is what is driving a lot of this, and certainly making a lot of our clients think about electric solutions and really trying to prioritize that. The last bullet point here, there's all, in addition to all those sort of local legislation and sort of mandatory requirements, there's been a lot of institutional and corporate goals from an ESG standpoint that are really driving this as well. If an owner or an institution has portfolio-wide or company-wide greenhouse gas reduction targets in their ESG goals, this is one very, very key way to get there in the future, and something that a lot of clients are looking at. We're talking about with them sort of in conjunction with these local laws and sort of how they align and what's the right way to address them. So again, those are the reasons why this is kind of what's happening and how we're having the conversations with clients these days. So again, all that kind of sets up what our internal process is and sort of our process with our clients, which is to set up a charrette, set up a conversation to kind of go through what their goals are, what their targets are, whether they're driven by the laws, driven by 2030 limits, driven by something else within their ESG for their portfolio. And then we're presenting options back to conventional sort of gas-fired systems and what the efficient electric systems might be looking like, where there's carbon savings, how much savings there is, and we're really kind of trying to focus on that and highlight that for our clients. And then our process is often this creates questions, unless you have a really, really savvy client. It's going to create questions which they're going to want to know a little bit more about the systems, want to know a little bit more about the longer term carbon impacts and limits. And then there's a little homework we'll do, and ultimately we come to a decision and choose a system for the solution. And so that's our process. We've been kind of giving a little bit of this history. It's not a whole lot of like energy or carbon 101, but we're making sure the client understands why we're talking about electric buildings. Again, many clients are right on board with this off the bat, but some are less familiar, have only heard about it and don't really understand what it means to them. So it's important to kind of walk through this and make them understand what's coming, what's here today and what's coming in the future, and how these solutions might help their building. So from there, I'm going to kind of switch gears a little bit, talk a little bit about technology. This is a designer series, so I wanted to kind of highlight a little bit what our experience has been in the market and kind of what we're seeing. Very quickly, this is by no means meant to be comprehensive, but there's two major technologies that are sort of the easy or quick answer to what's an all-electric building look like. Those two are Airsource heat pumps and variable refrigerant flow, or VRF systems. I am not suggesting these are the only alternatives. There's lots of other systems like heat recovery chillers and water source alternatives and ground source alternatives that we look at as well. But often these two are at least on the table, and sometimes the only real alternative for an owner, depending on what the building type is. I'm not going to talk too much about VRFs. VRFs are a little bit more straightforward and have been around a little longer. I think we've seen that creep into the New York market, starting at least probably a little longer than 5 years ago, and these days are a little more straightforward. I will talk a little bit about some of the case studies why that wasn't a great solution for the buildings that we were talking about, because they were something that we looked at. But I am going to talk a little bit more about the air source heat pumps, and the reason being is that these have, there's been some significant changes in terms of the technology and really improvements in that technology in the last, I would say, 2 to 3 years that we've experienced. And you know, what would have been a greater challenge maybe 3 years ago to design a system using one of these air source heat pumps has become more and more achievable recently. And I'm going to talk a little bit about that and why. So first off, an air source heat pump, I mean, this is again 101, most of you probably know this. It's essentially a system that is using air as the heat rejection or heat addition source to a water loop. These systems can produce hot water or chilled water, and some of them are simultaneous machines that can do both at the same time. We often design around a combination of those different module types. In the case studies I'll present later, I'll talk a little bit about what we've done there. But big picture, these are low carbon consumption. These are meeting that COP limit that I described earlier in terms of a system that is better from a carbon standpoint than as a fossil fuel boiler system. There is one of the questions we always get is, what does this do to my electric system? Is this a big, I need a much bigger electric system? What's the peak load going to look like? There is a marginal increase to the peak HVAC load that we've experienced with this system type. The peak draw in winter season is often slightly higher than the peak draw in summer season. But if you're cooling electrically already anyway with your building, if you have electric chillers or DX systems, the increase on the peak is marginal rather than substantial. It's not necessarily, or it's unlikely to change service size. It might just be some larger panels or circuits to these machines, but that's it. It's not anything dramatic. And what it does do is it kind of shifts when the peaks happen. Instead of being a purely summer peaking system, you're going to see summer and winter peaks that are going to approximate each other. That's what we've seen, and again, not surprising and consistent with lots of documentation that's out there. And the research that's been done out there. Many of you may have seen Urban Green did a paper a couple of months ago, and they have this actually quite neat tool that you can kind of walk through and look at different districts within the city to get an idea of when, as electrification happens, when those zip codes and when those districts within the city might switch to a winter peak versus summer peak. So that is going to happen as we move towards electricity as the heating source. But if we do it efficiently, it's not going to be dramatic. And we think it's something that can happen without major changes to infrastructure today. And then the last bullet point here is really what we've been seeing as the improvement in the last few years, which is the efficiency has been improving and the range at which these can operate has been improving. To talk a little bit about that very, very briefly, the two selections you see here on the screen, the left-hand one is one we had gotten, I think it was about maybe 3 or 4 years ago from a manufacturer. And the best we could get there was like 104, 105 degree water at 5 degree outdoor air temperature, which we're not going to design to less than or to more than that in New York City. There are conditions where we would experience higher than or lower than that, so we want to make sure we're able to cover the heat load, and not a great 100, 104 degree water as the output supply water temperature. You can design around it, but it was the other thing, you see that image, the pink or red is the operating range. We're right on the edge of the operating range. As an engineer, you probably don't really like to be at that selection point. It wasn't an ideal condition. Whereas on the flip side, the right-hand image is a selection we received that was just on a project we were designing last year that is showing, between -4 and up, 120 degree water is very achievable. This is a much more comfortable selection for us and something we've been working towards, and really sort of like what we've been seeing as the sweet spot to where we've been selecting this. The other note here is there used to be really kind of one manufacturer in the market here in New York. As we all know, one manufacturer is not ideal. It's tough to get competitive bids. It's not the perfect situation. In the last several years, we're seeing more and more vendors, more and more manufacturers able to meet these conditions. There's at least 2 that we've been dealing with. There are 3 at least that can do it, but then this module comment that I make down here is questionable for some of them. And increasingly, I know we're talking to many manufacturers, and there are more coming. A lot of them have products that are just about ready, but are still kind of getting ready to roll out across the US. So this is rapidly changing, and increasingly more and more are available in an efficient way. The note here that I'll make is there's the sort of the two notes in red. The first is, as many of you probably have experienced, the old New York City compressor rule, trying to be lower than 15 horsepower compressors to avoid the need for an operating engineer on site full time. It's a big deal in New York, and depending on the scale of the building or the type of the building you are designing, it could be a deal breaker if you're not meeting that 15 horsepower limit. So I would just caution to be careful as you're designing and selecting modules and selecting the conditions you're operating at. Warmer water might shift you into a larger horsepower compressor. We've found that 120 for this sort of 15 horsepower module is somewhere in the sweet spot. As we've been trying to design around 120 as the supply water temperature. You can get warmer water, and for a building that doesn't have a concern about an operating engineer, there are options to push that up. But this is something that, keep that in mind, keep module size in mind as you're doing selections. The other note here is coil, obviously at a lower temperature water and often with a lower delta T than you might have experienced with, with older fossil fuel burning systems. You got to think about how you're selecting coils. It's not the same coil you would have selected for 180, 150. So be mindful of that. Often that's an achievable thing. It's not something you have to worry about. You just have to make sure you're selecting the right coil. The one area where we see that is sometimes a limiting factor is just single row fin tube if you have a lot of glass, right? Single row fin tube with 120 water supply water can be challenged to heat a high load envelope. So you start to look at things like multi-row coils in the fin tube, or essentially some sort of airflow across that coil, some sort of induced air, or no longer a purely passive heating system. So a couple notes on the products that are out there and what we've been experiencing, and some cautions to think about as you're designing. And this is, just to continue my car analogy just a little bit further. I think we've had the old one, maybe it's the Tesla, and nothing against Tesla, but nowadays you can buy a Porsche Taycan, which is maybe I just like it better personally, but maybe a little bit of an improvement, and there's more people coming on the market. So this is evolving in a similar way to what is happening in the electric car market, just maybe a couple of years behind. Okay, so I'm going to dig now into some of the case studies. I don't know, Ben, if there's any questions. You haven't paused me here, so maybe I'll just keep going.
Well, I haven't seen any questions yet, but just for everybody out there, any questions you have, just type them in the question box and we'll get them answered.
All right, all good. I'll keep moving, but again, as Ben said, I'm happy to answer questions as we go. I won't take quite the full hour, so there's definitely time for discussion if we want. Okay, so now I'm going to dig a little bit into the case studies as we go. Okay, so I'm going to talk a little bit about these two buildings, which look very similar in a lot of ways. On the left, we have Rubin Hall, which is a dormitory at NYU. It's an existing building, historic landmark building in Greenwich Village. It's a great building, because of the landmark status and the historic existing building status, a little bit of a different challenge as in the building on the right, which is a brand new out of the ground student residence for Weill Cornell Medical School. Also a great building. Out of the ground meant, we have a little bit more flexibility, but there's different challenges from a design perspective that this one presented. So as we go through this, I'm going to talk a little bit about some of the things we did in both buildings, the things we did differently in the two buildings, and why we chose each of those solutions. First off, I'm going to talk a little bit about specifics on NYU Rubin. And just because this is a question I get all the time, especially from architects and owners, there's many things as we're doing a study on a building that we walk through as we walk through the options. What does this mean to me? How, what does this look like? Costs, energy, carbon, maintenance, etc. And we walk through all of that on these options. But one thing that is definitely a difference and sort of like something to get your head around and really get the architect's head around is what it means spatially and the space impacts to the building that are different than a conventional system. So I'm going to highlight that a little bit. This was the options we had looked at early on for the NYU Rubin Hall project. We started with, this is a job we were doing about 1.5 years ago. So we started with our conventional, which would have been a tower boiler water source heat pump system, very common for residential buildings in the city and elsewhere for a long time. We then looked at different all-electric options, the first being VRF system, which has its positives. And then we looked at two sort of variations on an air-to-water heat pump system. The first being sort of a hybrid with some local heat pumps within the building, and the second being just an all air-to-water heat pump building with fan coils.
Hey Jeff, we do have a question, and maybe it'll
Great.
help set the stage for some of the
That's
information coming forward. Sean would like to know, what is the source of the COP at 1.6 number as the limit for carbon competitiveness?
Great
Where did
question.
that come from?
Yeah, so that is based purely on doing the simple math with, I'm using the New York City Local Law 97 carbon emissions factors for, I'm comparing what, BTU of gas at the means from a carbon standpoint, like how much carbon is emitted by burning a BTU of gas and how many BTUs of heat you get out of that. And I'm comparing that to how many BTUs of electricity you need to produce a BTU of heat, and what the carbon content of that is based on the New York City Local Law 97 conversion factors for electricity, converting electricity to carbon. Does that make sense? So it's basically, I did the quick math of here's the carbon per BTU of heat with a gas boiler system, and I'm assuming 80-something% on the gas boiler and what the emissions of that is. And then I'm comparing that to what the efficiency of a 1.6 COP is and the electricity conversion with the New York City Local Law 97 limits. Does that make sense?
I will find out, and if there's a follow-up, we'll let you know.
Okay, yeah, let me know. So yeah, that's what that's based on. But anyway, so just comparing these systems and focusing on the space requirements, because this is a question we get all the time. And this is something I've walked through in other presentations in the past, but just to talk a little bit about the specifics, conventional boiler system, this was a landmark building, the Rubin Hall project, and sight lines and existing roof conditions and structure of the roof were all really important considerations. So the roof was a big concern here. So we had to really map out, could we do these systems on the roof of this building? We didn't have all the alternatives because we were dealing with a landmark facility. So we looked at what a conventional system would have been, and that would have been just a cooling tower on the roof, right? A very straightforward solution. We know what that looks like. Then we looked at a VRF system, which would have been a series of different condensing units outside on the roof located. We could populate them in different areas, which was a little bit of benefit, but it has its other challenges. And then we looked at the air source heat pump, which is the air source heat pump has to go on the roof. So we looked at what that would look like from a space standpoint, and also kind of considering what that would mean for landmarks. So the first one, the conventional system, the nice thing about this was those cooling towers fit pretty easily right in that upper right-hand corner of the roof. That was a setback roof. It was kind of removed from the street. Fifth Avenue is on the left, 10th Avenue is on the south side of this plan. So those are the primary view considerations for landmarks. So that was a nice spot to put it. It was a pretty simple footprint. I will say that it was the smallest footprint of the options, but it is the tallest. Most of you probably are familiar with cooling towers being pretty tall. So from a sightline standpoint, it actually wasn't ideal from that standpoint, but the footprint was much simpler and actually allowed us to kind of set it back a little bit. So it was straightforward from that perspective. The VRF solution, these are smaller and shorter pieces of equipment, so easy from that perspective, but we were looking at a lot of them populated across different areas of the roof. And then as I'll talk about it later, because of the height of this building, we actually were going to need to locate some on a second floor roof setback as well, due to refrigeration run limits. So another consideration, but definitely more footprint than the cooling tower on the roof, but shorter. And then the third alternative with the air source heat pump solutions, they are kind of in between in terms of the footprint, a little bit less than the VRF, a little bit more than the cooling tower, and also in between in terms of the height. That is something we looked at. This is ultimately the system that we did choose, and as I talk through the rest of these case studies, I'll explain a little bit more about that. But this was the solution for this building. It was something we were able to work. But just note it was a larger footprint. So if an architect's used to dealing with cooling towers on the roof, this is going to be a little bit bigger impact than a cooling tower footprint, and something that we're going to have to be aware of going forward, right? So definitely a conversation to have so that you're not shocking people as you start laying out roof plans. So then, this is sort of like what we ended up presenting. This is obviously carbon and cost impacts were a very key component of this discussion for NYU. As you see here, the energy costs between, I'm going to focus on the first two and the fourth one that we looked at here. The third one kind of ended up not being a great solution. But the operating energy costs were, similar. They're within $10,000 to $20,000 of each other, so not a dramatic difference between them. Obviously, there is a bonus there, but the first cost was definitely higher on the Airsource heat pump system than the tower or VRF system. But we were, and I'll talk a little bit more about the specifics of this later, there are some pretty lucrative incentive programs that really were able to kind of incentivize this to a pretty strong degree and get us some nice lucrative incentives that really made this more palatable going forward. So something we were able to work through. Yes, please.
We have some additional questions.
Okay.
So just to follow up on the last question, that did make sense, but there was a follow-up that the COP, it's still a point of contention, confusion among the building industry, i.e. non-engineers. So we need as many, well, questions are coming hard and fast now. We need as many knowledgeable sources as possible to publish this information and keep making this a point. So that's just for you and AKF. Jeff, I'll jump to your question in a second, but then Eric had a question. Seems like the only water-cooled system that was looked at was water source heat pump on the evap side. Have you guys evaluated water-cooled systems, but hydronic AHUs, FCUs on the load side?
We often look at water source systems. I will say with a water source system, you need a heat addition source to that loop, right? Your condenser water loop needs a heat source to do all your heating from it. And what we've found is challenging is what is that source if you're trying to do all electric? There are options. First off, if you're at a different site than, this building wasn't going to be able to do geothermal, given the existing building location. If you can do geothermal, you do ground source, that's a great solution, and we do that elsewhere. And that's one answer to that. We also, I think, increasingly in an existing building scenario where we're looking at converting an old building to a all-electric solution, we are looking at a phased approach where we often look at a water source heat pump as the solution, and over time phasing in what that heat addition source is. Some of those buildings have Con-Ed steam. We're starting with in the short term, Con-Ed steam can still be the heat addition to the condenser water loop. And over time, sort of phasing that into an all-electric solution if the Con-Ed steam is going to, either depending on how that works with carbon and the Con-Ed steam over the long term. Does that answer that question? We do look at it, but this was focused specifically on trying to be all electric within the building. That was one of the reasons.
So Jeff had a question. What is the break-even COP when you also consider the utility costs of electric versus gas in addition to the local I-97 carbon coefficients? So I think that is taking cost into consideration rather than just BTUs.
Important question.
I want to touch on that.
Yeah, important question. So I don't have a specific COP answer for that right now, but I will say if you look at just what's on the screen now, the annual energy cost comparison of these four options, the two that the VRF and the Airsource heat pump, so it's sort of like the second and fourth one on this list, those are a slightly lower utility cost than the first alternative. So that suggests that those COPs, those operating COPs were annually better from a utility cost standpoint. Now, the note there is the selections on those, the COPs at the sort of 5-degree outdoor air condition, I believe are somewhere in the range of the 1.6, 1.7, but annually, as it gets warmer out and they're operating at a 25-degree day, they're operating at a higher COP, and those utility cost numbers are taking that into account over the course of the year. So it's not a single COP number, but it is, annually these heat pump solutions were they're seeing more attractive. And I think the alternative to that is an all electric building, just electric resistance would certainly be a higher utility cost, significantly. So we've looked at that. I don't have those numbers right now, but it would certainly a higher cost.
Okay. On this, so this is another question from Sean, and then we have a question from Robert. On the system selection and roof plans, did the FD&Y requirement for a Q-01 refrigerant system operating engineer and 15 horsepower compressors factor into this decision at all? And then
Yeah.
I have questions on this at the end too, or thoughts. Go ahead.
Yep. So absolutely, and all of these modules that were looked at were all designed to address that, to avoid the operating engineer. They're all smaller modules, and intentionally so.
Mm-hmm. And then a question from Robert: as fuel prices increase and electrical kW, kWh rates increase, at what point will these new systems become more attractive to existing building owners? And do you see federal rebates coming for these upgrades as part of the Green New Deal wish list?
You know, I don't have a great answer for either of those questions. I will say, as for existing buildings, when we've been talking to owners, what I've seen right now is like when work needs to happen and sort of like when capital planning is looking at age of existing equipment, these solutions are viable, right? Even from a first cost and utility cost standpoint, they start to become viable, similar to what they are on a new building. It's always a challenge to go into an existing building and just rip out a system that's working fine, and putting something new, because there's the cost of doing the work in the first place. So that is a challenge. From a rebate standpoint, I'm unaware. You know, I for a while was tracking the federal programs that were kind of coming up. It's been a while since I've seen the latest, so I'm not entirely sure what's planned for the Green New Deal if and when that gets written. But I will say that locally in New York State, for sure, there's pretty substantial incentives for these system types. And I'll give some numbers in a little bit on these two examples.
Great. And then we had one last question, a follow-up from Jeff. This relates back to our January presenter, Charlie Jellin from Train. So many traditional refrigerants are being phased out due to high GWP. How does that factor into equipment selection discussions with owners for the longevity of their equipment?
Yeah, I mean, it's something we are continuing to talk to reps and owners about. I don't think that necessarily is any different for these types of equipment than it is for any cooling equipment, right? It's a similar conversation. I think if anything, because you know these heat pump solutions are a little bit newer technology or a little bit less common technology, the refrigerant is something that they're kind of revaluing what they can do with these already, and as part of that, refrigerant selections are our primary discussion point. I mean, one of the manufacturers out there that is making can do some pretty warm water temps, but they're using a non-conventional refrigerant to do that, and I think increasingly that's what we're seeing. I don't have an answer for like exactly what is the right refrigerant to look at these days, but it is something just where we're consistently asking that question of what is available and what's going to be available in the future. You know, should we be looking for the next refrigerant, not like what's only out there today when we're getting selections?
Okay, that's all we got for now, but keep the questions coming.
Yeah, that's great. All right, moving on. So again, just talk a little bit about these buildings specifically. To give a little bit of the details, they're real similar in terms of size and height and scale and operation, right? So 150, 160,000 square feet. We like that because it's a good scale for a sort of centralized water loop system, whether it's water source heat pump or air source heat pump. You know, it's not a real small building. It's also not a huge building. So the 30-ton, 15 horsepower compressor modules seem to fit well. It's a nice, the owners here didn't want to have a full-time operating engineer on a building of this scale, so that sort of played a role in our design discussions. The heights, similar heights, 17, 16 story, they're very similar height. What that did do is it meant VRF was a little bit of a challenge given the refrigerant runs and the length of piping we'd have to do to locate all the refrigerant or the condensers on the roof. We did have the option at NYU to put some condensing units at a lower setback roof, which is kind of hidden from the street. That has other challenges acoustically, but it was a possibility. On Weill Cornell, we looked at the alternative of locating compressors on the floors, so like carving out a corner to get some some air and air exchange on the floor. It was possible. What they didn't like about it, or what was a negative about it from the full design team standpoint, was we were going to have to essentially lose a bed per floor, which from Weill Cornell's standpoint was a deal breaker. Obviously, they're building this building to get as many new student housing beds as they can, and that was a pretty big detriment. So that kind of made that a no deal for VRF. Programs very similar, student residence. One of the differences, NYU is an undergraduate, so it's a much denser environment, and sort of what the amenity space is slightly different. And I'll talk about one of the roles that played in design. Whereas Weill Cornell is, it's graduate medical students. These folks are, it's not, your freshman year dorm. It's more of like an apartment setting. So it's a little bit different density and a little bit different in terms of the amenities that they were offering. But for both of those, the central system really was a positive. For an Airsource heat pump system where you have a single loop serving the whole building, that is a little bit of a challenge when you're talking about a condo arrangement in terms of how you bill and what that billing arrangement is. Not a concern here because of the student and it's a single owner kind of condition, right? The envelope performance, this is a similarity in that both buildings really pushed the architects in both these buildings, FX Collaborative on an NYU and Perkins and Will on at Weill Cornell, really pushed an efficient envelope. NYU is specifically pursuing Interfit, which is the existing building passive house sort of standard. A lot edit insulation, new windows, really a focus on performance of the envelope. Similarly, Weill Cornell is pursuing Zone Green under the 2020 Energy Code, so that's no easy task in itself. And also the envelope that's being selected there is not quite passive house minimum, but pretty close. So it's a really efficient system. What that allowed us to do is allowed us to sort of reduce and minimize our HVAC capacity and how many heat pump modules we needed. It also allowed for low temp hot water to be pretty achievable at the perimeter. We didn't have concerns with the kind of heat we were getting out of that water. It was something I mentioned earlier on. The Weill Cornell building is a valence unit system. So that is a system that does need that envelope to be pretty high performance for the systems to work. So that was a consideration. The other point there I'll talk about a little bit about this in a second, is resiliency. The high performing envelope did allow us to really kind of do some things in terms of like what we could do in a power outage. I'll talk about that in a second. That's a condition for both those buildings. The domestic hot water, I'm not going to talk too much about this here, but this is always a question on a residential building specifically. Domestic hot water loads are a very big load within a residential building. And it's a challenge from an all-electric system. How do you do that within the building? Where do you get your air from if you're trying to do a heat pump system? Where do you fit that? How much storage do you need? The fact that we did this Airsource heat pump or air-to-water heat pump for both HVAC systems allowed us to size our heat pumps to bring water to water heat pumps that did the domestic heating in both these buildings. So allowed all of the heat rejection or heat addition to be on the roof, and then have that loop feed into the water-to-water heat pumps that are doing the domestic loads. It did increase the heat pump capacity on the roof, but it did sort of simplify what we had to do on the domestic side and still give us a very efficient all-electric building here. So another important consideration.
Jeff, I'm not sure if it's just me.
Yep.
I think the bottom of the slide's cut off just the way it's presenting.
Huh.
But the domestic hot water, I think it says HVAC source.
Oh, that's all it says, Ben. Sorry. Yeah, that's just that's meant to say that it is the domestic hot water receives HVAC water as the source side. That was not. You're right. It's
Okay.
It's a little confusing, just the text there. But that is what that is. So sorry. Gonna keep going. So just in terms, I mentioned resiliency as a component here in a discussion on both buildings. One of the things we did is, so with both of these buildings, we're providing manual or mechanical ventilation air, tempered ventilation air to each residence through a DOAS with heat recovery, energy recovery systems. We are providing those with emergency power in both buildings. What that does is it allows us to provide some level of heating all year. My screen keeps on jumping around, actually. Did that jump for you guys?
Yes.
Yeah, I don't know what happened there. Sorry about that. It's very strange. I don't think I touched anything. Anyway, so what that allowed us to do is provide fresh air, tempered fresh air all year, even in the event of a power outage. That plus the really high performing envelope allowed us to create what we were calling a habitable space, even in the event of a power outage for a long period of time with the generator running. This is a graph of something we looked at for Weill Cornell. We did a series of different options where we could supply 70 degree, which is the normal condition from the outside air. We're just sort of supplying neutral air. We looked at if we could heat it to 80 degrees at the unit, get a little more heat out of it. And then we looked at sort of like different alternatives in the envelope. What we ended up with here is something kind of between the gray and orange, where we're able to maintain at least 60 degrees all year on a typical year in the event of a power outage. This is showing the indoor temperature in a typical student room if you lost full power, but we're able to run the ventilation air systems on the emergency in that power outage. So what this is saying, we're considering this quote habitable space. The students could stay there all the time, which is positive. I don't know what's going on with my screen here. Sorry about that. Keeps on kicking me out of slideshow, which anyway. Okay, so that's showing that we're able to maintain that space temperature throughout the year. What you're not seeing is the summer conditions. We were not concerned as much with cooling, although it does temper it a little bit as well. But these all have operable windows. The idea being, in the event of an outage, you at least have an operable window, which is considered to some degree habitable, right? Talk a little bit about the differences between the two buildings and sort of some of the key design differences that resulted. I already talked about this one, sort of the landmark versus the brand new building. I talked a little bit about the rooftop challenges. I could go on and on about that. That was a very big design challenge, but that was probably the biggest difference in terms of the physical requirements on these two buildings and what that meant for how we had to design and lay out the systems. I won't dig too much further there. I know we're getting close to noon. In terms of the program, the actual residences themselves are very similar, even though there's a different density in the two rooms. But the amenity space is a pretty big difference. The NYU project does have a second floor amenity. It is a student amenity for the folks that live there, but it is largely meeting space. There's like a common kitchen pantry area, but it's not super intensive space. It's more like gathering and a little less sort of intensive spaces on the second floor. It does have operable windows on that second floor. And then in Weill Cornell, on the alternative to that, the lower levels, there's sort of two below grade levels, has a much more intensive amenity program where they have, there's a gym, there's a yoga studio, there's some fitness spaces. So spaces that needed full conditioning, heating and cooling year round. We couldn't get away with a full-on two-pipe system. One of the conversations we had early in the design of both these projects was two-pipe versus four-pipe. Two-pipe is something we don't like doing often, as a lot of folks do. There's concerns about heat season, cool season switchover. But for a student residence, it's something that most folks are used to. Quite common actually in a student residence environment. So it was something that both buildings agreed to within the residences themselves. And on NYU, it allowed us to create a fully two-pipe system because of the program. Whereas on Weill Cornell, we did have to provide a partial four-pipe system for those amenity spaces. And I'll talk a little bit about the differences there. And it did provide an additional complication. But obviously, the two-pipe versus four-pipe system is a pretty big difference in terms of cost. So we were mindful of that and tried to simplify that as much as we could for the residences themselves. The other component here that we looked at was how we condition the outdoor air at the DOAS. We looked in both buildings at sort of a local VRF coil condition design versus a central heat pump, so fed from the heat pumps, glycol coils in the outside air units. We changed that a couple times on Weill Cornell, and largely driven by cost. I'll speak about that a little bit in a second. Again, so just touching on the landmark
Jeff,
roof.
we had one question from our friend James Kish about, and this will depend on how you define the occupancy of these buildings, but just touch on the fuel that you used for the emergency generator for these buildings.
Yeah, they're both gas fired, and that is a result of the occupancy rating that we were allowed. And I apologize. I forget if this is. I always have a mind block here, whether it's R1 or R2, which allows natural gas versus fuel oil, but it is natural gas.
I think R2.
R2, yeah. Sorry about that. So yes, they're both natural gas. Okay, so going on again, roof was a very complicated solution at NYU. One thing to note is the acoustics became a challenge here in addition to just space. The acoustics of the heat pumps was something that this building is located pretty close to a neighbor just to the north. So we did have to go through that with the manufacturer, and the attenuation was definitely a pretty hot topic for a while. So definitely be aware of that if you're next to an existing building. Is going to be something they're a lot harder than cooling towers, as you might expect. Okay, I talked a little bit about this, the 2-pipe versus 4-pipe. Again, NYU, because of the program, allowed us to do a purely 2-pipe system, whereas, well, Cornell, we have sort of this hybrid 2-pipe, 4-pipe, 2-pipe, purely 2-pipe on the student residences, but a 4-pipe for the lower level amenity space. These are the risers. You can't see these super well, and that's kind of by design. I didn't want to go into too much detail here, but the idea being, there's sort of 2 key takeaways, I think. The first being we do have sort of the middle modules on the risers excuse me, the right-hand side of modules are the simultaneous heat pumps. That is allowing us to do simultaneous heating and cooling for some of those systems as the first source when we do have a simultaneous load from the 4-pipe system, where we do not have simultaneous machines at NYU because it is purely a 2-pipe system. So there is no simultaneous load given the 2-pipe arrangement. So that was one difference. The other thing to note here, and actually this was true for both buildings, at the Weill Cornell project, we are providing the source side of the domestic from what we're considering the 4-pipe loop that goes down to the amenity. In both conditions, what that means is the source side of our domestic water heating systems will go down as low as 40 degrees because we're providing 40-degree chilled water. So you do need to design your water-to-water heat pumps with a 40-degree incoming source load, something that these heat pumps can do. It's not a concern, but definitely make sure you're doing that. It's actually in the winter, those machines will be more efficient because they'll be provided with 120-degree water. So they are more efficient in the winter than they are in the summer. That's at the domestic load because those are off this 4-pipe system loop. And in NYU, they're off the 2-pipe, but the 2-pipe's in cooling in the summer. But they also do sort of take some heat out of that loop and do a little bit of pre-cooling back to the air source heat pumps in that summertime. So you get a little bit of a simultaneous effect there. So just something to note. And this was one of the more complicated aspects of the Weill Cornell design, was mapping out this 4-pipe system arrangement because it did add some complications, but it ended up being a pretty good solution, and it allowed for the simultaneous machines to operate pretty efficiently when we had that simultaneous load. The last thing I'll talk about in terms of the comparison was the difference in the air source heat pump. One component to think about is, whether you're doing a VRF or you're doing a central system DOAS. We ended up changing at Weill Cornell a couple times, and that was sort of just circumstantial. The way the building was designed, it ended up being a cost savings to look at the VRF coil. I don't think that's necessarily an equipment cost delta, just the way the design worked out and sort of where the equipment was located. So just be mindful of that and something to think about. But I think the biggest benefit that we were seeing with the VRF solution on the DOAS system was the controls, right? Especially when we were talking about a 4-pipe system, a 2-pipe system, you're talking about switchover. Switchover is tough if you're trying to do neutral air from a DOAS system. When you have the DOAS on a VRF system, it's totally divorced from that 2-pipe loop. It can do whatever you need to at the coil within the unit, and really allows you to provide that tempered air year-round without any consideration or concern for outdoor air conditions and what the 2-pipe loop is doing. So ultimately, we are on both buildings ending up with a local VRF coil at the DOAS, and I think that's a nice solution for these 2 buildings. So that's kind of the end of the descriptor. If there's no questions, I'm gonna just jump to sort of a tail of the tape punchline here, where we ended up. Actually, Ben, I had one last slide. If we can go back to that. Did I lose the screen share? Something's happening on my end here.
Nope, we see it.
Oh, okay, cool. I don't know, I lost it for somehow. Okay, so this last slide here is just showing where these 2 buildings ended up. As you might expect, they both had very ambitious LEED and sustainability goals. Reuben is going for retrofit. They both are pursuing LEED. Reuben is looking at 16 LEED energy points, whereas Weill Cornell is looking at 5. That's a pretty big difference. The big difference there is due to Reuben Hall's existing building envelope, which we're able to take credit for from lead perspective. So that's the real win there. Weill Cornell is a pretty designed to the New York City 2020 Energy Code, so it's a pretty good envelope to start. If you look at those carbon numbers, those numbers are tough to understand off the bat, but they're both significantly below the 2030 local law 97 limits. So doing really quite well from a carbon standpoint. And over time, as the grid gets cleaner, these are all electric buildings, that number is going to go down as the grid gets cleaner. And as you might expect, the absolute energy in carbon from Weill Cornell is a little bit better than the NYU absolute number. Again, that's just due to it being a new building and having the opportunity to do some things with the envelope that were a little more challenging at NYU. And then the last piece here, which I've talked about a few times, the incentives were really lucrative. The one we're focusing on is Con Ed Clean Heat Program. We've been dealing with that and looking at that for a number of projects recently. You see these numbers, we're looking at around 3 million for NYU, over 1.5 for Weill Cornell. Again, the delta being the existing building envelope is the starting point at NYU, so these are both performance-based. So Weill Cornell is a little bit tougher baseline, it being a new building, but both of them are getting really lucrative incentives and a really nice savings from Con Ed through this Clean Heat Program, which is really trying to incentivize this exact kind of heat pump design. So that's all I had. That was the kind of the summary.
Well, that was fantastic, Jeff. We sincerely appreciate it. So for everyone, I put it in the chat, but if you, when you exit this, there should be a survey, fill that out. You get PDH credits. We'll get you certificates within a few days. And there should be a feedback survey. So we'd love to hear from you. And if you have any further questions for ASHRAE or Jeff, please reach out to us at ashraenyc@gmail. I put it in the chat. That's ashraenyc@gmail. And we look forward to seeing you at the next meeting and the next designer series. So Jeff, sincerely appreciate your support of ASHRAE as always.
Great. Yeah, thanks, Ben. Thanks for having me.